While our last video talked about all the things that happen when we look at visualizations at a glance, our brain is processing a lot of information throughout the entire time we're working with a visualization. In this video, we'll cover some of the later phases of perception and cognition that occur after we've had a chance to first look at a visualization and as we really start to dig into our data. So, visual attention kicks in when we really are actively acknowledging and searching through the data displayed in a visualization. This typically happens after about 250 to 500 milliseconds. Our attention typically starts at whatever element of the display popped out at us, but interesting things happen once we actively are paying attention to a visualization as well. Attention, in its most simple definition, is essentially where are we looking? And while we feel like we get a sharp and clear picture of everything within our field of view, in practice, we actually are only getting a sharp picture of a small element of our visualization, just that central 2 degrees of what we're looking at. So if you want to understand how big this is, you can hold your hand out at arm's length and look at about the width of your thumbnail. And that's the area within your field of view where you're actually getting the most information and the highest resolution. What's happening on the edge? Well, outside of that central view, we're getting kind of a blurry, statistical, lumped together representation of what's going on in the visualization. So what we can do is we can design visualizations that work well with different kinds of attention to help guide people towards the information that they need to find. For example, we can, just like when designing for GIST, we can look at more of these blurred images and see what kinds of information are people likely to see in the periphery. There are 2 kinds of visual information that we might want to design for, top down and bottom up. When we're dealing with bottom-up attention, we're letting the visual features, the colors, the shapes, the sizes of a visualization guide what we're looking at. This is similar to when we're doing browse or explore tasks where we're looking at the data and just trying to find what's interesting. When we're dealing with top-down attention, it's our knowledge that guides what we're looking at. Think about this like visual search. We're looking for specific elements that we might care about. And it turns out that we can actually shift the visualizations that we use to design for these different kinds of attention. For example, in 1984, a pair of scientists named Cleveland and Miguel asked people to engage in a top-down visual search task. They said, you have 2 elements, data point A and data point B, and we want you to estimate what the value difference is between data point A and data point B. So roughly how much bigger is B than A? And based on the responses to this question from a series of different visualizations, they were able to create a ranking that allowed them to rank visualizations from the most effective, things like position and length, to the least effective, lightness and color channels. So this is a fabulous way to think about how to start choosing the most effective way to represent the most important dimensions in your data. But this relies on, again, that idea of top-down attention, that idea that knowledge is guiding what we're looking for. So we know we want to find A and B, and we know we want to compare A and B. How might these rankings change when I'm using more of a bottom-up approach? Well, a pair of psychologists, Sachs and Tversky, asked this exact question, and they would show people graphs like this bar chart, and they would say, describe what you see. And generally speaking, people would say B is larger than A. But if I take that same data and represent it using a different visualization, so the line graph here, what people would generally say is, oh, the values are increasing. So people are attending to different features of these visualizations here when I have a bar chart and I have 2 discrete objects and making comparisons that inherently beget these kinds of discrete outcomes. Things like A is bigger or smaller than B. Whereas if I have a line chart, I'm paying attention to the line, and therefore I'm paying attention to the slope of the line and seeing if that slope is increasing or decreasing. So the takeaway here is that how we represent data will affect the conclusions that we make. And this is especially true with bottom-up attention, where we may not be searching for particular elements of interest, but instead people are just browsing the data to find the important elements. So the next piece of visual search and attention I want to talk about briefly is a phenomena called change blindness. So it's all fine and dandy trying to explore a visualization, make sense of, and read data if the data stays static. But one thing that happens over time is people will often change their representation, or you might even see visualizations that integrate animation. So I want to show you real quick an example of a popular technique that's using animation to visualize data. So this here is an example of what is called a bar chart race. And you'll notice as values are changing over time, the bars are moving, they're shifting, they're rearranging. There's a lot going on here. And as you're visualizing this, and we've seen this time span from the late 1960s to the early 2000s, I might ask a question like, where was India ranked in this data in 1984? Well, that's kind of a hard question to answer, because when we answer those kinds of questions and when visualizations have changing data like this, it's going to rely on what is called our working memory to make sense of our data. And so when we're relying on our working memory, we're relying on a fairly fallible mechanism. So I want to show you a quick demonstration here of why working memory can be a little bit tricky.
This is a test of selective attention. Count how many times the players wearing white pass the basketball. How many passes did you count? The correct answer is 15 passes. But did you see the gorilla? This video.
And I promise if you go back and you watch that video later, I've got the YouTube link here, the gorilla was there the first time around as well. But this is an example of just this ability of people to only pay attention to a very limited number of changes in any one time, and also our ability to track and record and remember those changes. So this is why I would encourage you, if you are thinking about using animation in your visualization, be very, very careful with how you use animation. It can be engaging, but in practice, it's often very difficult for people to use. You can only pay attention to a small number of bars at one time, and you can only remember so much about what's going on in the scene. So once our attention is kicked in, we'll often engage in a process that is called visual search. So visual search occurs when we're visually scanning an image to find items of interest. Essentially what happens is we can think of our attention like a flashlight in a dark room. We're moving our flashlight around to see what elements are there in our visualization, what elements of our data are there. And we can rely on something to visually stand out as a function of its salience. Think about this in the same context as pop out. Things that are very salient tend to pop out. Things that are moderately salient are more likely to attract attention. Things that have low salience are unlikely to attract our attention. So we can actually manipulate salience to try to support visual search. One careful caveat to keep in mind is that oftentimes when we're visualizing data, we're trying to visualize multiple dimensions at once. And visualizing multiple dimensions means that dimensions can interfere with each other. That is, if I represent data using one visual channel like color, that might interfere with my ability to correctly search for, attend to, and estimate data in another visual channel like size. In general, this concept is known as separability, this idea of how do we actually search when we have multiple channels present in our visualization. Typically speaking, if we choose encodings like using position and color, that's going to be very, very easy to separate. Whereas if we choose dimensions like how much red or how much green is present, those are going to be much, much harder to separate. So we might choose to prioritize pairs of dimensions that are easily separable. And then as our data gets less important, what we can do is we can start to look at less and less separable channels for representing those additional data dimensions. One other way we can use this idea of multiple channels to support different kinds of analysis tasks are through what are called redundant encodings. So when I use a redundant encoding, I'm encoding the same data dimension just using multiple channels. And these multiple channels will support search and inference over different visual dimensions. So for example, here I'm encoding my Y value using position, using color, so the values are getting darker as they get larger, and using size. The marks themselves are getting physically larger as the values get larger. One trick that can emerge, though, if you try to put too much information in the same chart, is something called visual clutter. Visual clutter occurs when you have either too much stuff, or the way that stuff is represented or organized makes it harder to perform a given task. So many of us have seen the network hairballs, where it's like all that interesting network relational data and all the connections are so noisy you actually can't make heads or tails of what's going on in the graph. And this idea of visual clutter has inspired some classical guidelines in visualization. For example, the data ink ratio says you should minimize the ratio of you should maximize the ratio of data visualized to the pixels used. In other words, we want to try to communicate as much data as possible in the smallest number of pixels. One thing I would encourage you is this is definitely not a hard and fast rule. If we followed this to a T, every visualization we'd have would be a scatter plot with no axes and single pixel wide marks. So this is kind of a rule of thumb, but there are two more actionable techniques or strategies that we might have for managing clutter, and these are aggregation and organization. So when we have aggregation, what we're doing is we're taking lots of data and we're finding ways to simplify the representation by grouping data together. So for example, if I care about where the different classes of points are in the scatter plot on the left, one thing that I might do is I might use some aggregation. So I might do something like this technique here called hex spinning, where I divide my visual space up into hexagonal bins, and then based on which points are most dominant in that bin, that gets assigned to the color of the hexagon. Then I can remove any points that are redundant with the background color and just leave my outliers for a little bit of additional context. So this is an example of aggregation. I have a much simpler display here, and if I were to ask you where are all the blue points, the purple points, the green points, the orange points, it's much easier to point that out because we've smoothed over the information, we've reorganized it and aggregated it in a meaningful way. Another technique that we can use, you might recall from sorting you might recall from interaction when we talked about sorting. Data that is better organized makes it easier to find things. And we can see that in this example here. So take a moment to look at this heat map and notice which color do I only see in one grid cell of my heat map. You might notice that the only solo color here, the only lone color, is this magenta, this purpley lavender magenta here. But if I take this exact same heat map and I reorganize it, I can very quickly find where the solo magenta color is, right here in the same spot. This is the exact same data, just presented in a different way, and it makes it much easier to figure out where that oddball is. There is so much more to learn about how we can use the ways that we perceive the world to drive effective visualization techniques. I would encourage you to take a peek at the readings and at other resources to try to figure out how can you optimize your visualizations for the kinds of tasks and questions that people are trying to answer with their data. But we're going to wrap here, and in our next unit, move on to some basic concepts around representing more complex ideas like uncertainty.